Okay, so welcome back, everybody, to the SPACEMON 2020 second session. The second session will be covering atomic oxygen sensors and magnetometers. So I will hand you over to Sophie Desolier from Onera. Sophie, your time starts now.
Okay, thank you. Can you hear me now? Yeah?
Yes, loud and clear.
Okay. So good morning, everybody. So my name is Sophie Desolier from Onera, the DEFI department in Toulouse. And today I will be presenting some works about an active detector for atomic oxygen, which is called RESISTAC. So let's start with a few words about atomic oxygen, which is in fact the main component of the residual atmosphere in LEO, and which is produced by the photodissociation of oxygen molecules by the UV from the sun. And the interaction of AO with surface material mostly results in oxidation and subsequent erosion of surface. As you can see on this picture, you have example of the Hubble MLI and some samples or the MLI of MEDET that was on board UTEF ISS. So obviously this chemical and physical damage to mostly polymeric materials alters surface characteristic and degrades the thermo-optical and mechanical properties of material. So what is the context and main motivation to develop an active AO detector? In fact, it is twofold. At first motivation was to improving predictive tools, especially in case of exposed complex geometry. You have here on the top left the overall principle of the approach we develop to investigate effect of geometry, realistic geometry, and how to estimate atomic oxygen flux in such a context. And as you can see, there was one critical point to address. It was to monitor a secondary atomic oxygen flux behind geometry or in a realistic, let's say, geometrical context. Because in fact, a large part of the incoming flux is re-emitted, let's say, or reflected, and is at the origin of multiple reflection that can locally enhance the erosion rate of material. So this monitoring helps understanding the mechanism at ground during flight measurement as well, and as a basis for correlation with predictive tools and models. The second motivation was about applications in sub-LEO missions that are developing very rapidly with mega constellation, for instance. You have here on the bottom right the density of particles, atomic oxygen, but also nitrogen, O2 molecules as a function of the altitude. And as you can see, the lower the altitude, the higher the density of atomic oxygen, and there's decades, order of magnitude with increase of density. So in such a context, the recent observation have shown very strong discrepancies between erosion rate between prediction and measurement. It was, for instance, reported by Kimoto from JAXA, and based on SLAT's data. The second point here is also the synergetic effect that is observed between oxidized surface, AO oxidized surface, and the collision with high energetic nitrogen or oxygen molecules. And here it is, let's say, expected. Here again, we have in a worst case flux condition, and it was observed at ground that there must be very strong increase of polyimide erosion with a factor about 3 due to this synergetic effect. So these 2 or 3 examples illustrate the reason why for us it is of very high importance to develop active monitoring of the environment and to be able to couple this environment monitoring with the measurement on the effect in orbit. So on this slide, we have a non-exhaustive list of the different devices that are used for monitoring atomic oxygen in orbit. The monitoring is mostly performed using witness samples that allows to measure atomic oxygen fluence by measuring a mass loss of the sample. So of course, obviously, that requires the return of the sample. Okay, but most of flight data on shuttle or ISS, for instance, have been realized using witness sample because, of course, it is simple, cheap, lightweight devices and almost very low or no power consumption. Regarding active devices that can be monitored from, let's say, in real time, there's a possibility to make atomic oxygen fluence and flux measurement. We've got it QCM, for instance, or actinometer, catalytic probe. But of course, it is more complex because it requires an electronics for the acquisition of, for instance, frequency shift or resistance or temperature parameters. You have also mass spectrometer, which are much more complex, of course, but provides multi-species data, which is very important and interesting. So in this context, we propose a multi-layer devices we call ResistStack because it's a resistance measurement that would, let's say, lie in the category of simple, cheap, lightweight, and low or no power consumption devices. So this detector principle is shown here. It consists of multi-layer devices. So we have metallized Kapton films that are stacked and connected electrically. So the whole structure, in fact, the whole structure behaves like several resistors in parallel. And each time a film is fully eroded, Kapton film is fully eroded, you have the rupture of the resistance, associated resistance, and the equivalent overall equivalent resistance show a step increase. So, because Kapton erosion rate is very well known, the resistance evolution and fluence can be correlated, in fact. So that is the principle of this detector. And so it has been developed since 2013 with the support of CNES. We started with a feasibility study, of course, and different prototype and pre-testing. So the last details I can add here is that the metallization is a small silver film, in fact. So this is the structure of the detector. What is nice here? It's a cross section of a 5-layer structure. And it is based on space qualified material and PCB process, standard PCB process. So in this case, we make use of Kapton AC films of 12.5 micron that allows to monitor fluence atomic oxygen in this range, few 10 to the 20 up to 2 to the 21, with in fact, the metallization, as I've already mentioned, silver metallization, which is very thin. It's about 100 to 150 nanometer. This is what it looks like. The overall dimension is quite small, 3 by 4 square centimeter. And in fact, the detection area is about 2.56 square centimeter. And as you can see here, this is the metallization. Then you have here, you can see it is manufactured, each manufacturing batch allows to realize 10 devices at the same time. So recurrent costs are quite low, in fact. Then this is some ground data, because we had the first testing, AO testing, at the Montana State University in 2016. So here you can see the monitoring of the equivalent resistance as a function of time. And we could check with this testing that a good reproducibility of the detection. So each time you have this step increase here, there's a fluence of about 410 to the 20 that has been received by the detector. And we could also check that detection time is very rapid, in fact, and much more lower than the time to erode one layer. So ensuring a good accuracy of detection. And of course, considering the operation of this kind of detector, detection is required to capture the time of erosion of one layer. Here you have the thermal response of the detector that was realized during thermal vacuum and air pressure thermocycling realized at CNES in this range from minus 25 degrees up to plus 90 degrees, which is quite could validate the thermal functionality of our detector. Here you have the equivalence resistance, and here we have monitored also the resistance of each sublayers. Okay, and what is interesting, it's considering the evolution of the silver, the metallization resistivity with temperature. The very same detector that is used for air detection can, let's say, also use for monitoring temperature. So using this device, we have both capabilities. This slide is about the project we have now at the moment, because we have been selected, Resistec have been selected to be part of the Euro material aging experiment developed by ESA and CNES. And we have the support of CNES to develop two experiments, let's say, on the SESAM panel, let's say, which fly aboard Bartolomeo module from 2022. And as you can see here, there's two configurations, 2D and 3D. 2D will allow to have a direct exposure of the detector here that will be positioned in RAM, okay, with the maximum field of view. And on the second 3D, let's say, configuration, we will have two other detectors that will be monitoring indirect AO beam. By indirect, I mean the direct beam will be reflected by target materials, selected target materials, and the point is to investigate the geometrical effect and monitor the secondary, let's say, AO beam. So here you have on this schematic the view of these two experiment in one, let's say, and with the weight of the detector itself, and with the assembly, the overall assembly. So with this kind of configuration, the aim will be to really improve the knowledge of the local AO environment, and considering that on the same experiment there will be other, let's say, witness samples, we will be able to correlate environment and material erosion. Okay, so this is my last slide. I guess it was quite rapid. This is a summary. So Resistac is an active AO detector, which is based on space qualified materials and PCB process. So manufacturing tools are available. So it's there. We have low recurrent cost to manufacture these detectors. It's easy to operate. It's monitoring of resistance as a function of time, let's say. It's a low power and mass detector, and of course low data flow. There's not the need to have acquisition rate very high. It combines AO detection and temperature monitoring capabilities. So far, we have let's say threshold detection of 410 to the 20. Depending on the Kapton layer that are used and the number of layers that are embedded into the resistance. And of course, for the operation, there's a field of view requirement and datation that is required. And in the near future, we have this flight opportunity on Euro material edging, but we are also investigating different configuration on CubeSat and nanosat witness. And of course, we investigate as well the need for design adjustment. I mean, adapting the overall dimension, the detection area, number of layers, and so on. Thank you for your attention. And if you have any question.
Thank you for your presentation, Sophie. Yeah, we have 3 questions. The first one is coming from my colleague, Mark Millinger. Mark, would you like to unmute and ask your question?
Yes. Does it work? Do you hear me?
We hear you.
Great. I was wondering if impacts of small particles like debris also lead to, let's say, false signal, which is basically the sectioning, I think, of these Kapton layers. So first, is it a background? And second, can you distinguish atomic oxygen erosion from such impacts?
Of course not. Once the film, the silver film is that there's the rupture of the silver foil, let's say. Of course, it is considered that we have an erosion. Okay, it's the same signature, in fact.
Okay, so you basically rely on the fact that with the small area, the chance of having a debris impact is low over time?
Yeah, exactly.
Okay, thank you.
Okay, there's 2 more questions for you. The next one is from Diren Kataria. Diren, would you like to ask your question to Sophie?
Yes, I have 2 questions. One is, where is the atomic oxygen testing carried out for Resistac? And the other one, I'm not sure I missed it, but is the resistance measurement continuous? So you're continuously measuring the resistance all the time?
In fact, the testing has been performed at the Montana State University at Tim Minton Laboratory. So it's the same equipment that of LEOX 2, in fact, at ESTEC. Exactly the same source. Okay, and regarding the second question was about. Sorry, can you repeat?
So the measurement of the resistance, is that continuously happening? So you're just continuously monitoring the resistance?
No. In fact, we only need to detect the step increase in terms of resistance, and the erosion rate of Kapton in the O would be well, the rate is low compared to any shift of any let's say radiation degradation of a device or so on. So let's say measurement once a day or once every 12 hours, sorry, that's much enough. So most of the time there's no acquisition. It's like kind of passive, but you have to repeat the measurement, let's say once every day.
Okay, so it is about roughly once a day.
Yeah, but depends on the flight configuration. If you want to monitor re-entry configuration, probably you will adapt the acquisition rate to what you want to measure exactly.
Okay, thanks.
And we have one more question from Adolfo Aguilar. Adolfo?
Yes, I have a question about the tested lifetime under thermal cycling due to thermal fatigue for CTA difference between the Kapton layer and the silver layer. Have you tested the lifetime of the device?
I don't remember. For me, it was about 100 cycle. Let's say 100 cycle in air pressure and 10 in thermal vacuum, something like that. It was aimed at investigating qualifying the device for the Bartolomeo flight, in fact.
I see.
Okay, well, thank you very much, Sophie. And I think now we will move to our next presentation, which is given by Diren Kataria. Diren, would you like to share your screen? I think it's coming now. Okay, Diren, your time starts now.
Okay, thank you. Thanks for that lovely talk, Sophie. That was set a lot of context for some of the things that I'm also going to talk about. One of the instruments that you mentioned in your talk about atomic oxygen is an electrostatic analyzer, and this is what I'm going to present. A quick introduction. I am employed at the Malad Space Science Laboratory, which is the Department of Space and Climate Physics, UCL. And most of my activities are part of the in situ detection systems, which is one of the 4 instrumentation programs that supports our science activities. Pretty exciting time, actually, for space environment stuff. We had Solar Orbiter launched early February, doing a lot of work with UC Mention in the morning on the Lagrange L5. There's the SMILE mission, so a lot of space environment science, space weather science, plus monitoring. And what I'm going to talk about is 2 CubeSat-based missions, and one of the past CubeSat-based missions that uses the ion and neutron mass spectrometer that we built at MSSL. The main region of interest for both CERSI, QB50 and Discoverer missions is the very lower thermosphere. And the aim there has been to do a lot of science of the lower thermosphere. It's one of the regions that is being very poorly studied. And that was the motivation that we started with on QB50. And there was 36 satellites that were launched from QB50, with a whole bunch of them launched from the ISS. And there was an atomic oxygen sensor called FEPEX from Dresden. And there were 9 of our INMS sensors that are shown in the picture here that were flown on QB50. QB50 was launched from the ISS, so that's the sort of region that it covers. We were left with 2 flight spares on CERSI, on QB50, which we are now flying on a follow-on mission called CERSI. And CERSI is actually going to be launching in that sort of altitude range, 500 and below, in fact. So that's a little bit higher than I intended. And this is a schematic of the ion and neutral mass analyzer. We got an ion filter that allows us to reject ions. Neutral particles go straight through. You ionize them and use an electrostatic analyzer. And then we ping pong between ion and neutral particle mode. On QB50, we did achieve a pretty impressive 220 grams for this complete device. But it was mainly tuned for the sort of dominant mass species in that region. Here's a table of performance of the INMS. And as I said, it's designed mainly to monitor the dominant species, and we have the capability to be focusing on, let's say, the NO mass group or the N2O NO mass group, or both, in fact, depending on our cadence requirements. More recently, we've also added RAM and crosswind capability, and that's implemented in Discover. So I'll talk about that a little bit later. Currently, the instrument actually does not have a fly-through geometry. There's electronics sitting at the back here. But for future missions, we are looking to relocate the electronics so that it behaves more as a fly-through. And that should help, in fact, in terms of all the erosion elements that Sophie talked about here. Unfortunately, QD50 does remain unfinished business for us, because out of the 9 instruments that were flown, only one of them gave partial results. All the CubeSats were built by different universities and student groups around the world, so we had very limited number of CubeSats that actually returned science data. But we did get science data from the QB50, the Phoenix satellite, and that's what is shown here. Unfortunately, the satellite was Y Thomson spinning, so it wasn't 3-axis stabilized. So every time we went through the RAM direction, that's what we got. That's the energy, which was, in this case, mainly atomic oxygen. So we tuned the instrument so that it would look only at atomic oxygen and nitrogen, but there was so little nitrogen that we don't expect anything to see that here. And there is some element of wind measurement that we are trying to get out of it, because we can get vertical winds possibly from this spinning configuration. So that's what is being worked on right now. We did have these 2 flight spares, and we've been fortunate enough to be selected to go on the follow-on mission called CERSI. It's a DSTL-NRL collaboration, and we are part of the IRIS payload. Steve earlier mentioned one of the radiation detectors from SSTL, which is also here. Another payload from the University of Bath and us at INMS. There's more details about the CERSI mission, but so it's hopefully we will get more data with the QB50 instruments. And in the meantime, we also were fortunate enough to get further funding to take this to a Mark II, where we have implemented a time of flight capability. And we have delivered this to go on a CubeSat, which is part of the Discoverer project. And the project is doing both aerodynamic maneuver demonstration whilst monitoring the environment with our instrument. And we're actually also supplying a separate instrument for a ground-based atomic oxygen wind tunnel that is being built as part of this this project. And in this case, it's going to be launched from the ISS again, so it will be in a QB50-like environment, and hopefully that will give us more. I did mention about the ping pong operation. So when that element is turned off, you're in ion mode. Ions and neutrals go through, but the neutrals don't get ionized, so they go straight through, whereas the ions. And then we pong into the neutral mode where this element is turned on. So the ions are rejected and neutral particles make through. Some ground calibration data from that flight unit that we've delivered. There's an analyzer constant of 2.6 in there, reasonably good energy resolution. And this energy resolution, combined with this time of flight, is good enough to give us very good separation of the N2, NO, and O2. A quick look at that's what some data from, in fact, that was the QB50 Phoenix satellite, and you can see that with the 5 eV ram velocity plus additional ram velocities and thermal temperatures, the distributions are quite broad. So with only an energy measurement, it is very difficult to pick out winds. And one of the motivations for Discoverer was to be able to measure winds. So that 6% energy resolution is overlaid on here. And using the combination of time of flight and energy measurement, we believe we should get pretty good wind measurements down to about 50 meters per second for the ram direction. For the crosswind, we actually then have a slightly different technique. So what this slide is talking about is the resolutions of the time of flight region and how we are building histograms. But just a slightly closer look at crosswind measurements, because that's quite an important element that we are aiming for this kind of instrument. So we did a lot of simulations. I unfortunately don't have data for this. We have to wait for Discoverer up there. But we did a whole bunch of semi-ion simulations to demonstrate that we can get good crosswind measurements. And the technique that we are using is 2 separate apertures in 2 different look directions, and then the data from one overlapping with the 2, and by dividing one by the other, you can extract a measure of the incoming direction of the plasma, and in that way, that parameter then leads us to a measurement of the crosswind. And when you put all the numbers together with the sort of simulations that we did, we actually get a 1 sigma error of less than 10 meters per second, for a plus minus 400 meters per second wind. So that's quite an impressive element from a science point of view that we hope we'll be able to achieve. So a quick note is that we're also building this for a ground-based measurement. And the nice thing is we then get an end-to-end demonstration on the ground, but we can also look at, for example, degradation of the detector in atomic oxygen, and look at individual subsystems, and look at several aspects of making the sort of wind measurements, etc. So both of these going on in parallel. The INMS for Discoverer launching in May 2021. Currently, the instrument has been delivered. AIT is progressing on the CubeSat at GomSpace. The satellite is being built by GomSpace. So just to summarize, pretty strong heritage, a lot of miniaturization activities going on. The INMS suitable for atomic oxygen, both going on CERSI and Discoverer, but we also have the ground-based unit where we hope to be testing several aspects of this. Most of the components in here are COTS components. So we should get also a good demonstration of how well we can use them. But we do have high reliability systems from our other mainstream flight projects like the Solar Orbiter and the PLA that we've been talking, and a lot of those components, at the expense of higher mass and power, of course, can still be utilized for better. And obviously, it is an attractive instrument not only for space environment monitoring, but also for space science, because you can study a range of these masses with it. I did mention QB50 remains unfinished business. We hope that in future a similar constellation will go up there and finish the job in that very, very low environment. The Discoverer, just a quick note that it's not only looking at the space science element, but there's a whole bunch of cross-disciplinary applications of Discoverer, like aerodynamics, etc. The INMS in particular, of course, has a lot of cross-disciplinary applications besides the space science, which is environment monitoring in LEO, and there's a lot of space weather interest in doing that. And also for ground-based diagnostics, for example, for electric propulsion systems. So it's quite a suitable, it is an instrument that's quite suitable for several different applications. Just a quick I'll slip in the fact that because the LEO is quite an attractive area for a lot of Earth observation missions, there is this conference, but I'll leave that in the slide. A photograph of mostly the QB50 team, but we have a bunch of people that are additionally also working on Discoverer. Not a complete photo of the whole team, but it's quite a large team, and I do always love to show this slide, so I will leave it at that slide there with the deployment of the QB50 satellites from the IS, and hopefully in 2021 we will have a few more photographs like this, especially since Discoverer is going on from the ISS, and we will have a few more pictures like this.
Thanks, Darren. Very, very nice presentation and nice images at the end. Didn't see any questions in the chat for Darren. I don't know if anyone has a question, but if they do, please just unmute and chip in. So then maybe I ask a quick one there, and I saw mention of Daedalus and on your slide. So is this is it a payload for Daedalus as well, or some derivation is, or I've misinterpreted that?
Oh no, it is a candidate instrument that we are proposing. We have proposed and studied for the Daedalus Phase 0 study. So yes, it is one of the candidate instruments that we have proposed for Daedalus. I think the decision is today and or tomorrow for down selection of Daedalus. Okay. And it is the perfect targeted orbit for an INMS like this one, because it does go down to the sort of 150 kilometer regime, where MSSL does have a very strong UCL has a very strong interest in that region of the thermosphere.
Yes, of course. So I guess if it's selected, then this measurement is a requirement, and then they will decide which of the candidate instruments they will select for it. Is that the
that is
correct
correct?
interpretation?
Yes, that is correct.
So I don't know if anybody else has a question. I'm just scanning down the attendee list right now. If not, I think we will move on. At this point in the agenda, I had established 5 minutes just for general questions on atomic oxygen sensors. It was mainly as a buffer to give fair enough time for questions. I don't know if there are any more general points that people wish to raise on atomic oxygen sensors.
So can you hear me now?
Yes, we hear you now.
Okay, I connected via an external audio link, so I'm sorry. I need an additional permission for speaking.
No problem. Okay, I think your presentation is coming. We see the screen with your browser.
So can you see the presentation now?
Yes, we do. Thank you. Please begin.
Okay, so my name is Olaf Hilmeier. I would like to talk about the SASMAG project. SASMAG is a short name for Service-Oriented Spacecraft Magnetometer. The magnetometer was launched 2 years ago in the frame of the ESA Space Weather Program. This presentation is focused mainly on the instrument hardware, the lessons learned, and maybe useful improvements for follow-up projects. SASMAG is designed or was designed for magnetic field measurements on satellites without a dedicated magnetic cleanness program. No long boom is necessary. The idea is the measurement with 2 flux gate sensors mounted on a short boom, and we have 2 additional sensors mounted on suitable places between magnetic disturbers inside the spacecraft. The measurement data will be corrected on board with the help of the data of the 2 platform sensors, so that we have data available in a very short time. So we speak about minutes that we have corrected data on ground. The team, 4 groups has worked on this project. Maxon was responsible for the development of the DPU, for the flux gate electronics and the box design. The Space Research Institute in Graz for the RMR electronics, the DC data cleaning on ground, and for the complete ground processor. The Technical Universität in Braunschweig, the Institute for Geophysics and Extraterrestrial Physics for the flux gate sensors, the boom, and for the AC cleaning algorithm, and the magnetometer group from the Imperial College in London has provided the RMR sensors. SASMAG has a modular concept and is composed of 4 standard magnetometers. In principle, each of these magnetometers you could use as a standard device on the satellite is equipped with a 28-volt DC-DC converter and with an RS-422 telemetry interface. All magnetometers are connected to the DPU, and the DPU is connected to the satellite telemetry system in case of SASMAG via KSAM. KSAM is a Korean Space Environmental Monitor. So next slide describes the DPU. It's a full redundant FPGA-based CRISP processor system with an RS-422, with 5 RS-422 interfaces, 4 to the magnetometer clients and 1 to the spacecraft, with an EMI input filter with a powering condition unit for the magnetometer, with switches for the individual powering of each magnetometer, and with a power switch to operate the flanging bolt for the boom deployment. We have housekeeping measurements for all primary and secondary power sites, voltages, currents, temperatures, and so on. But the main task of the DPU is the data acquisition from the magnetometer and the execution of the cleaning algorithm. For that, the DPU starts synchron the measurement in all magnetometers. The magnetometer sends with 128 Hertz the data to the DPU. Next step is a rotation of all vector in a common coordinate system and the scaling of the vector, followed by the execution of the cleaning algorithm. And last step is averaging to an adjustable data rate. So power consumption of the DPU is less than 1.5 watts. This slide shows our standard design magnetometer for scientific spaceflight magnetometers as used for Mascot on board of 2 LATAN satellites, on board of JUICE, and last but not least SOSMAC. We have a range of 65,000 nanotesla that is adjustable to the requirements. We have a noise level of less than 10 picotesla per square root hertz, and we have a fixed data rate, vector rate of 108 vectors per second. The ARM-L sensors have the same range and the same data rate. In the case of SOSMAC, we have connected to one ARM-L electronic 2 sensors, the 2 platform sensors. So SOSMAC, this slide shows the complete stack of the instruments and shows the dimension, mass, power resources needed for the complete stack. The high mass is also caused by the massive Wald thickness of 4 millimeters. The instrument will currently operated in space in 1 Hertz 5 vector mode. That means we have 1 Hertz vectors from each magnetometer and 1 onboard corrected vector. Higher data rates with 4 vectors at 16 Hertz were only available during the commissioning phase. The telemetry rate is unfortunately limited from the satellite side. In the future, we hope that we can send data, corrected data, as is the correction for stable. We can operate the instrument in a 4 Hertz mode with only onboard corrected data. So the satellite was launched approximately 2 years ago in a geostationary orbit. The boom deployment was in January 2019, and we have the nominal operation since the 25th February 2019, and planned nominal operation time of 10 years. So lesson learned. The good message is that the cleaning is possible even if the satellite was not designed for magnetically cleaned. In total, the 4 interference fields of we can eliminate the interference field of 4 sources. We see it in the next slide. The onboard cleaning works with the SOSMAC hardware and also with the algorithm, and the achieved data quality is used for scientific application. This slide shows an example data plot. You see the flux gate data in black from the outboard sensor, and gray from also the boom-mounted inboard sensor, and in red the onboard corrected data. So we see mainly 4 disturbers, the so-called midnight jump, 16 o'clock EUT is midnight Korean time. We see a big jump to this time. We see steps. We see spikes every 10 seconds, and we see also some high frequency disturbers. So these 4 disturber sources will be cleaned on board, so that the result is the red curve. The table shows the 4 disturber types and values in detail. So how works the cleaning? In a first step during the commissioning phase, we downloaded raw data from the magnetometer, and correction matrix was data mined on ground and uploaded to the spacecraft, and the correction of the data will be performed on board. The correction matrix were determined with a principal component gradiometer, AC cleaning techniques. It's developed by Dragoș Constantinescu from the TU in Braunschweig. So things that did not work perfect. So 3 of the interference sources are eliminated by the boom-mounted inboard flux gate sensor, and only 1 by using of the 2, or in principle 1 spacecraft-mounted RMR sensor. The problem was, or the problem is, the higher noise level of the RMR sensors. With a higher noise level, you have to reduce the distance between the sensor and the disturbers, but not too close, because the inhomogeneity of the disturber field, and you have, during the accommodation of the spacecraft sensors, or the planning for the accommodation place for the spacecraft sensors, not real pictures of the disturber levels and the correct or the exact locations of the disturbers. So, and the quality of the corrected data will be increased if also has the spacecraft sensors the same quality as the boom-mounted sensors. Each measurement error, each noise, each temperature behavior or temperature dependency remains in the final data product. In case of SOSMAC, we have up to 5 nanotesla temperature drifts, variations by a daily temperature cycle over more than 100 degrees. That is complete. That was complete unexpected for us. So this plot, this slide shows the DC offset drift of approximately 5 nanotesla caused by the temperature change between minus and plus 50 degrees. And the correction of this effect, it's very difficult, because that looks like science, and currently we have an ongoing investigation to reduce this sensor offset oscillation to less than 2 nanotesla. So alternatives for future multi-sensor arrangements of satellites is the substituting of the RMR sensor by using of flux gate sensors. Perfectly or ideally with the same electronics, so have the same sensitivity, the same frequency gain, the same timing, and that would be the best solution if you have the resources available. If you have not the resources, maybe the using of another type of magnetometer. We use this type of magnetometers in altitude control system. This magnetometer has an identical sensor, but with a small size electronics. The range can be adjustable to the same range as scientific class magnetometers. The problem here is because the small distance between the sensor and the electronic, you have a higher noise level. We give the value that's lower than 100 picotesla, but the most of the devices has between 50 and 16 picotesla per square root hertz. So during the preparation to this talk, I found a table in an ESA study from 2011 with the requirements to the magnetometer for space weather measurements. And these requirements are completely fulfilled by the Fluxgate sensor with a science class electronics, but not with a small magnetometer, with a small Fluxgate magnetometer, with a AOCS magnetometers. So, summary, SOSMAG is a multi-sensor magnetometer on board the GeoCompass mission 2A with a nominal operation since approximately 2 years. We have calibrated data in the time frame of 5 minutes. The DC requirement of 5 nanotesla is met. But the AC, we have violations in the AC requirements. For AC, the requirement was a correction better than 1 nanotesla. That is not achieved yet, but we have automatically flagged in indication for violations. So, and we have an ongoing study for cleaning of the temperature-driven offset oscillation. Thank you. That was the end of my presentation. More information, especially through the cleaning algorithm and the data quality, you can find in the listed publications. So that was all from my side.
Thanks very much, Olaf. So we have a few questions on the chat for you. The first one is coming from Andrea, who was our previous talker. Andrea, want to unmute yourself and ask the question? Okay.
No, thanks.
Ah, you don't. Okay. Fine. Then I'll skip to the next question. Or did you want me to ask the question? Let me know in the chat. I'll skip to the next one for now. It was from OHB Sweden FSJ. Now, I don't think that's Niels.
It's Sten.
Hi, Sten. I couldn't guess that from FSJ, but okay, please ask your question.
Our satellite will just barely take your boom. We have our longest dimension is 1.2 meters. What deployment angles can you support? Is the nominal deployment angle 90, but could you support 180 is the question?
I think we have 180 degree deployment, or what is the question? It's the angle, I guess.
Yes.
Yes. That is, you see it in this picture. That is the launch configuration, and after the deployment, we have. Oh, sorry, I'm wrong. Yes, we have now 90 degree. No, not yet. Not with this design. We cannot support 180 degree with this design.
Okay.
We can only deploy in the configurations that we have in the deploy configuration 90 degree.
Okay, thank you.
Okay, then our next question was from Manuel Metz. Manuel, do you want to ask your question?
Yes, thank you very much. I was just wondering about the requirement for a sampling frequency of 1 second. Is this driven by the orbit? Because it seems to be, to me, it seems to be quite high for geostationary orbit. And if you would lower this, could it help you to further improve the data?
Unfortunately, we are in piggyback, and we are part of another instrument, the Korean Space Environmental Monitor, and so we have a very low data rate. That is, yes, it's limited by the spacecraft side, and in principle, SOSMAC can support it. Also for the corrected data, telemetry rates up to 128 Hz for all magnetometers.
Okay, then we had a question from Sergio Terzo. Sergio, do you want to ask your question?
Yes, thank you. Since we understood from this presentation that the AOCS platform magnetometer can be used to improve the SOSMAC performances, do you have an idea how many this would be needed?
How many? It's difficult to give this. The problem is that the noise level of the arm Earth sensors with 200 picoteslas is too high. So for the data correction, the perfect solution is to use really 4 times the identical flux gate electronics, and only if you have not the resources, or you will use this hardware on an alternative for a small satellite, then it is useful to use this small AOCS magnetometer.
Okay, thank you.
Okay, then I just wanted to check, maybe Andrea, maybe you were answering questions on your presentation and I misspoke, but if you had something to ask for Olaf, now would be the time.
No?
No?
Sorry, the question on the chat?
Yes.
Yes. I already answered. Oh, okay, there is another. Yes, this will change the power efficiency and the overall power needed to each electronics. So yes, it will affect the magnetic field. Yes.
Okay. Right. So do we have any more questions generally on magnetometers before we break for lunch? Please.
Actually, I was trying to find the paper that Olaf posted in 2020, but I was not able to have a look at it, so I'm really interested in it.
Olaf, maybe it was on your last slide, was it?
The last slide.
I think that's where you had the references, no? Yeah.
Ah, great.
Now, I'm hoping that these presentations should be made available to everybody. At the moment, some of them are not accessible. It depends on the permissions given by the people uploading, and I have to double check those before we ensure they are available to all attendees. But I will do that separately. If there are no more questions, then I would just like to thank again. Oh, was there another question? Oh, Greg has his hand up.
That was from the previous presentation, the hand.
Okay. Your hand should be tired by now. So I just want to thank again all of the speakers, especially for keeping to time, and for everyone who asked questions. For a workshop such as this, the questions really are important, and it's a bit more challenging online, but please don't be afraid. Also, I would like to thank Francois Piet, who has been doing all the timing for all of the presentations this morning. And with that, I think we can break to lunch. And after lunch, we will proceed with microparticle instrumentation and data exploitation related to microparticle instruments, which will be led by Daniel Hendricks and supported by Fabrice Cipriani. So have a good lunch and see you all at 10 minutes to 2 CET. Thank you.